Hey, Mr. C, coming to you from the home studio. I had put the related rates problem, fun related rates handout on the website. I think I did it Friday. Uh, if you haven't worked on those two problems, I'd like you to try them right now. Pause the video, try these problems, and then come back to the solution, okay? All right, so these are problems. I don't know. I woke up one morning and I had this rhyme on my mind, so I wrote it down. As you can tell, it was a while back. Let me read it with you. Fred was a man that liked to paint. It was a bet that he wouldn't faint if he painted the Watertown bed red before it was time for Betty to bed. Fred stood atop a 10-meter ladder, leaned 8 meters off the base of the tower. Poor Fred's ladder slipped at the base and started backwards. Fred's descent began in earnest at 0.5 meters per second. All right, I'm reaching a little. I'm using artistic, poetic expression. How fast was the base of the ladder moving from the base of the tower before Fred met the ground with a smack and a holla? Okay, so you got a water tower. I think you know what water towers look like, right? You got stuff going on, supports underneath, whatever. Here's Fred's ladder. Now, they tell you it's a 10-meter ladder, right? Here's Fred. Uh, Leaned 8 meters off the base of the tower, okay? So this is 8, right? So Fred probably propped himself up a little bit too much. Too much angle going on here, Fred. So what am I giving you here? I'm basically giving you a right triangle. And if you do the Pythagorean theorem, you should be able to tell me that the height would be 6 meters, right? Which is about 18 feet. So, Fred's gonna hit the ground, but it's not earth shattering. It's not career ending. It's just a holla. Okay. So what's happening here? Think about what's happening. The ladder is slipping. Uh, this is going this way, and so the base of the ladder is going this way, right? So think about this. dv or dy, this is the y, if you want, the y component, the x component. dy dt is actually going to be negative, isn't it? Fred's descent is negative 0.5 meters per second. Okay, what do we want to find? Find how fast is the base of the ladder moving from the base of the tower. Okay. Do we have an equation that relates those lengths to a right triangle? I think you know we do. And we would say x squared and y squared equals 10 squared. Now, some of you might be thinking, well, why didn't I put in 6 squared plus 8 squared equals 10 squared? Well, you're right. That's true. At this moment, okay, at the moment, Fred is painting the water tower red, but at the moment that it starts to slip, it's 6 meters and 8 meters. And now it's slipping. Now the 10 meters is not going to change. The ladder is the length of the ladder. It's not shrinking. It's just reorienting. So if you will, if this was my ladder, it's doing one of these. Okay? So the length of the ladder does not change. But the y component is shrinking, and as the y component shrinks, notice that the x component expands. Okay? All right, so here we go. That's why this stays the constant, because the ladder doesn't change. And we go 2x dx dt here, and 2y dy dt here, equals the derivative of a constant is always going to be 0. Okay? All right, and now plug in what you know. Plug in what you know. We know x is 8. 8 times 2. We don't know dx dt. we know y is 6, and we know dy dt is 0.5, negative 0.5. All right, so what do we get? I get 16 dx dt equals plus, no, it wouldn't be plus, would it? Minus a half times 12, so half of 12 is that'll be negative 6. So dx dt is going to be 6/16 meters per second. Okay, and you need to test it to make sure it works. You know, if this thing's shrinking, of course this thing's growing. So if you would have had a negative here, and this came out negative, you knew you did something incorrect. All right, let's look at the other problem. I'm not going to pause it. We're just going to keep rolling. That was pretty creative, wasn't it? It came out of this mind. Yes, it did. Now, in the past, in years past, we would form groups and we would try to concoct our own fun-related rate problems in class. That would be kind of a difficult thing, even in the best circumstances. Okay, so we'll just say that we tried and didn't, or something. Sorry, not sorry. Jack feels deflated. Jack loved to kick his kickball. The only problem is it became small. It had a leak. It began to deflate. At a cubic inch per second, it was almost too late. You see, if it was originally 16 inches in diameter across, at what rate was the ball deflating? At half the original radius. Was the measured radius fading? Oh man, is that good or what? Don't you want to write that down? Don't you want to put this in a frame next to your bed? All right, here we go. First of all, you need a function. You need an equation. He's kicking his kickball. What kind of a shape is the kickball? We know it's the volume of a sphere. What's the volume of a sphere? 4/3 pi r cubed. The only problem is it became small. It had a leak. It began to deflate at a cubic inch per second. So what is changing at a cubic inch per second? Volume, right? So now there's a little bit of a puzzle here. If it was 16 inches in diameter originally, at what rate was the ball deflating at half the original radius? Was the measured radius fading? Oh man, that's good. Half the original radius. Well, what's the original radius? It was 8. Half of that is 4. Okay, find dr dt. All right, here we go. dv dt, you should be able to do this by now. We've been doing these. We've been plowing through these. So, right, 3 times 4/3. So I'm going to get 4 pi r squared dr dt. Well, how many variables? Uno, dos, tres. How much info? Uno, dos. See how that works? -1 has to equal 4 pi. What? 4 squared. dr dt. And then you get -1 over, if you want, go ahead, multiply it out. Units are linear though, right? Be careful of your units. Yeah. All right, there you have it. That's from my creative mind.